Welcome to NPTEL. I am Jayanto Das from IIT Kharagpur, Department of Metallurgical and Materials Engineering, and I will be teaching advanced materials and processes. So, today we will be mostly focusing on the development of materials, chronological order of development, and how these advanced materials has been started to be developed by several scientists and different companies. In addition, the relative importance of this material compared to all other kind of engineering materials will be also discussed. At the same time, we will try to look at what is the relevance of metastability in this aspect. Now, here if you kindly have a look this slide towards advanced materials, evolution of engineering materials, in the x axis we have plotted year of development from 10,000 BC to 2020 expected, and in the y axis we have the relative importance. You will see during that period of 10,000 BC, the ceramic was very much popular and polymer was very much popular, except very little part of gold has been used. Throughout the different years, the stone, flint, pottery, glasses, cement, refractories, Portland cement has keep on developed, and the relative importance also has decreased during that period. Polymer has also decreased because the importance of metal keep on increases. So, let us say the cast iron, steel, alloy steels has been keep on developed till let us say something like 1960s. At this time, the zirconium, titanium alloys has been also developed along with super alloys, lightweight alloys. But after 1960s, if you kindly have a look, then again the relative importance of ceramic material has increased, polymer has also increased, and composites also has increased. So, here high modulus polymers, let us say transformation toughened zirconia, pyroceramic has been developed, including some high temperature polymers, conducting polymers. But instead of the plain carbon steel or mild steel, the advanced steels like dual phase steel got some preference and has been developed. Another example was micro alloyed steel. So, upon very minor addition of alloying elements in steel, how we can develop and how we can increase the strength of the steel 3-4 times. So, that was basically the idea. Super alloy even though has been started to develop in 1940s, but very new super alloys, here new means the super alloys which can survive at much higher elevated temperature from let us say 800 to 14,000 degrees centigrade. At the same time, even though glasses was very much popular in ceramic like oxide glasses or polymer glasses, but metallic glasses has become in the market and also the researchers try to develop. So, here the development is slow, but the quality control processing they has been more focused and the research has been done in that way, even though the relative importance become a little bit less compared to polymer, ceramic and composites. And therefore, we can try to understand that during these years 2010 and 20, a huge effort has been given towards these advanced alloys. And interestingly, most of these advanced alloys are metastable in nature. However, if we have a look, then we can see the importance of this material and why one should focus on this. Here I show you another plot. Here the percentage share is shown in the y axis, and x axis this is so far different kind of materials which has been used or underused, and in 2030 the predicted materials to be used. Kindly have a look here, almost 52% of the steels has been used, and majority of them are let us say low quality steels, mild steel, plain carbon steel, or some part of the alloy steel, tool steels, so on. However, the market of high strength advanced steel will increase. So, almost like from 15 to 38%, and this is a expected by 2030. At the same time, the aluminum alloys or advanced high strength aluminum alloys should be developed, and which will almost cover an increase by 140%. The high strength steel will increase 150%, and therefore, there is a basic need and general awareness among the engineers to put effort and to develop these alloys. At the same time, non lightweight alloys will not change too much here. Let us say something like nickel alloys, titanium alloys may be there, and some part where the carbon fiber are very less, you can see here. On the other hand, there is another big target of developing high strength or advanced magnesium alloys, which is expected to cover almost 5% of the total materials market. And therefore, you can see that we definitely need a very wide and general awareness on in this area. So, we first try to understand that what is the metastability means. You may have heard about the terminology metastable, but we need to discuss and try to look at what does metastable means. Here you show a free energy versus variables in the system plot. We take a very simple example like a ball which is kept in such a condition, and we can also keep the same ball under such a condition. Definitely the energy is higher here than here. So, there will be a net decrease of the energy, which is often called in terms of thermodynamics, that there is a net decrease of the free energy. However, to go from this place to this place, we need some activation barrier, and the activation energy controls the kinetic of the process. So, from one state to another state, let us say state A to state B, if the state has to come from A to B, it has to come through such a condition which looks like a unstable condition. So, if we keep the ball here, there are two probability, either the ball may come into this B or it may go back to A, and therefore, the equilibrium, this terminology means that any small change in the system must cause the free energy to rise. Let us say here also, if you consider position A, here if we want to increase the position of the ball in any of the direction, then the free energy will rise. The same condition is also valid here. So, you can have a look, if I try to push the ball up, then the free energy will rise. However, this is a saddle point configuration where system may go either any of these two ways. So, thermodynamic equilibrium for the Gibbs free energy at a fixed temperature and pressure is similar to this mechanical equilibrium which I told here as a potential energy of a ball held at different positions. So, a very small change in the condition under an unstable state will cause a spontaneous change towards a new metastable or stable equilibrium. Here this we define as a stable, however, there may be more or more such condition where it will be more and more stable, but in every cases we need some activation energy, and this activation energy will dictate the kinetic of the process. Let us try to understand the matter a bit more in detail. Here you see a two-dimensional plot with free energy versus the variables. In this plot, the same plot, however, we try to show you in a 3 dimension, where we can think about, let us say, 2 different variables along with the free energy. So, extensive variable we have plotted here, and these are often called as sub basin, or this is something like a mega basin in a system. So, this model has been adopted from a very well known model called energy landscape model, and we again put these 3 different condition of a ball where free energy will rise, and this is called as a saddle point configuration. So, once the system has to pass through this saddle point configuration, we need a activation energy, and there will be net decrease of the free energy. So, in this basin anyway, if we want to lift this ball, there will be a net increase of the free energy of the system. This is from a very recent literature. However, we may also have a chance not only to go from this place to this way, but we can also push the system to move from this way to the left, from right to left we can also go, but at that time the situation may be little bit different. Let us have a look. Here I just reverse the plot and like to show you that from a stable configuration to a more metastable configuration we can also move. Here we have shown in terms of the mechanical equilibrium of ball, but this could be a cluster. This could be a cluster. A cluster means I am talking about atomic clusters like HCP, hexagonal closed pack cluster, or FCC cluster, or body centered cubic cluster. Okay. And from let us say one crystal structure, the system can move to another crystal structure, okay, and it has to pass through some equilibrium. So, from a stable material we can also develop some metastable material if we provide some activation energy, and this definitely the activation energy appears like a Arrhenius type of equation. Even though there is a net increase, but we can consider such a situation where there will be a little decrease of the energy from a saddle point configuration. So, this is very much important understanding one should need for developing the metastable alloys, because here metastability means a microstructure, maybe a crystal structure, maybe a phase, and all could be a metastable. Now, let us look at what is the importance of the kinetics in this process. Since I said the kinetics, if we can restrict, then we can hold this metastability of a system. As an example, we all know about window glasses. These are oxide glasses like silicon dioxide with some of the additives people add to make some color, and that is also under metastable state. However, a glass always try to crystallize if some activation energy is given. So, here we are talking about a glass, and here this is a crystal. So, from a glass to crystal we can change the state. So, which will also lower the Gibbs free energy. However, the crystallization kinetics here that is governed by this activation energy, and the crystallization kinetics can be very slow at room temperature, and that is why all these glasses in big temples or mosque or anywhere you will see that the window glasses are stable for thousands of years, because we control the kinetics of the process and we restrict the kinetics, so that the glass remain in the glassy phase for hundreds and thousands of years. And this is the importance of developing all these advanced alloys. And since we are metallurgists, we try to look at the metallurgical aspect in this kinetic and to control the kinetics of this process. As I said that the hindering of the kinetics is very much important, and how we can hinder the kinetics, like the microstructural change. It means, as an example, I may have grain of let us say some 50 nanometer, and there are some 2-3 nanometer some precipitates are there inside. Okay. And if I have to keep this microstructure in this way, then we should simply avoid the grain growth and also the precipitate. There will be no change in their crystal structure, the phase should not change, and then only we can retain such kind of microstructure, very fine microstructure of 50 nanometer. And this is the importance of the metallurgical aspect to control the kinetics. And in this way we can develop newer and newer alloys to the system. However, I should first talk about some of the very common examples of metastable alloys. As I said, the precipitation hardened alloys are also metastable alloys, because the precipitate always tend to grow and reduce the strength, or if under certain thermodynamic condition temperature, let us say here precipitate dissolve. So, we need to retain those precipitate in aluminum copper alloys or silver copper alloys, so that we can retain their properties, mechanical properties. Beta titanium alloys is also very famous as a metastable alloys, because alpha beta phase transition is important to retain all these properties of such lightweight alloys, which is often used as aircraft and high temperature also. The shape memory alloys are also a very common metastable alloys, because here austenite to martensite, this phase transition is very much important along with twinning. Along with twinning is important to get the shape memory behavior in alloy system. Definitely glassy phase is metastable, so far I have already discussed. Retaining the nano size grains in nanocrystalline or nanostructured alloys, they are metastable alloys. Also high temperature, there are several metallurgical tricks we use, so that the precipitate should not grow at even at elevated temperature above 1000 degree. Then only we can develop such high temperature alloys. Same as superalloys. Superalloys is also one type of high temperature alloys. Lightweight alloys, which is also a common example of some precipitation hardened alloys, and also cast aluminum alloys. Now, what about steel? Yes, steel is also a metastable alloys. So, in case of steel, we all know that the alpha iron carbide is a metastable phase diagram. Okay. So, this iron carbide diagram is a metastable phase diagram, because there we have iron carbide, and if you increase the temperature and anneal this sample, then all time this alpha iron and graphite will evolve. So, iron carbide will simply decompose into two phases, that is alpha iron and graphite. Graphite is more stable. So, steel is also a metastable. So, if we develop advanced steels, we can call them as advanced metastable alloys. Now, let us have a look at some of the historical events in metastable alloys. Simply metallic glasses, here we use the terminology metallic because the bonding itself is metallic, and Professor Paul Duez, he was a professor of Caltech, and Clement, of one of his postdoc, was studying at that time gold silicon alloys and vitrified on a conducting substrate and did some X-ray diffraction studies. Okay. And they show such kind of halo pattern that I told in the last class. Okay. So, this is 2 theta versus intensity plot, and they saw the disappearance of any crystalline peak, and at that time people were clueless that even in case of metallic system one can obtain a glassy phase. So, that was almost the initial discovery of metallic glasses in 1960s. Okay. And after long period in 1993, Atakan Pecker, who was a PhD scholar of Professor Bill Johnson at Caltech, they have reported the first synthesis of bulk glasses. Here the bulk, this terminology or this bulk, it basically means in any dimension 1 to let us say 2 mm. Okay. In different books they define in different way. So, it is something like 1 to 2 mm in any dimension, and we call them as bulk metallic glasses. So, larger dimension. Another big historical event was the quasicrystals that we discussed in the last class, where there is only rotational symmetry exists, but there is no translational symmetry in the lattice. So, in India during 1978, Professor G.V.S. Sastry, who is still a professor at IIT Benares Hindu University, he was studying aluminum palladium alloys, and he find that twin like diffraction, but at that time it was not told that it was a quasicrystalline structure, but very similar alloy in aluminum magnesium. Dan Shetman from Israel Institute of Technology, and he basically reported the first new structure as quasicrystalline structure in 1982. And we are very glad as a material scientist that he won the Nobel Prize in 2011 because of the discovery of the quasicrystal. So, this is a bigger and bigger, let us say, news in case of all these material scientists. And I show you here the people who are the pioneered this field in case of metallic glasses, and this is Professor Paul Duez. This is a picture taken in 1974, Professor Dan Shetman from Israel Institute of Technology in 2011, and Professor Johnson from Caltech in 2000. And they almost pioneered this metastable alloy field actually, and contributed more and more, and there are many scientists who has also contributed and developed the field so far. Also there are many other advanced alloys which is under the development, like shape memory alloys. As I said, this is a smart metal, or let us say because it can remember its shape, initial shape. So, if we change some of the thermodynamic condition like temperature, pressure and so on, then the material regain its old shape. So, Arne Olander, which is a Swedish scientist, in 1932, he first discovered a pseudo elastic like behavior in gold cadmium system, and this was a really big achievement. So, pseudo elastic here means actually that if we take a stress versus strain plot of such material, then the material shows such kind of deformation okay, at temperature which is greater than austenite finish temperature. Okay. Austenite finish temperature means it is all in austenite. Okay. Austenite is a phase which transform into martensite, and then if we unload it, we saw that the same material comes back, and this is somewhat a very large importance in this particular aspect, that it looks like a plastic deformation, but it is not plastic, it looks like elastic, because we can get this back, because here martensite transform to austenite and here austenite transform to martensite. So, during deformation austenite transform into martensite and the martensite transform into austenite during unloading cycle. This is unloading. Okay. So, this is also a great achievement in this particular case. Now, another big discovery in this direction was 1962 from Naval Ordnance Laboratory from US, and they developed the nickel titanium shape memory alloys, which is known as nitinol. And this nitinol is a very commonly used for several applications like heart surgery, very small antenna and robotics, and these are also a category of smart materials or functional alloys. From 1905, the high temperature alloys keep on developing because of the turbine engine, and Professor Moss at Cornell, they along with General Electric, they have developed these superchargers, which is also a part of this development of super alloys. A very common lightweight alloys are aluminum alloys, which is used for aircraft component. So, that has started almost development in 1930. If you have a look to any of these aircraft and Boeing, let us say this is a Boeing 777, and so you can see that starting from the body stiffener to body skin to lower wing of the surface, here the upper wing of the surface and floor and forgings, all are these are all titanium alloys, aluminum alloys. So, all of them are very important as a lightweight, because if we have to design such a aircraft, then we need very lightweight and very high strength. And so, these are developed because of the demand during those periods, and also still those materials are under development. So, I show you these 5000 series, 6000 series and so on. There are some of these alloys are non-edge hardenable and some of the alloys are edge hardenable alloys, where zinc, magnesium, silicons are added as per the purpose. So, at the same time the high temperature alloys are also developed because of such kind of demand, and you can have a look that the temperature here is something like 1800 at the nose of a space plane, national aerospace plane, like 1780 degree centigrade temperature and 1450 degree centigrade temperature, and we need to develop these alloys, and therefore, people need develop the high temperature alloys. So, like here I show you some of the example with the material surface temperature with the approximate year of the use of the aero engines. So, like here you can see the 2010 or 2020, the mostly developed materials are the ceramic matrix composite, even though the single crystals and directionally solidified superalloys has been developed, but their temperature is relatively lower than the carbon composite, and therefore, all the spacecraft, the outer surface is made out of carbon composites. Here also I show you a plot with strength to weight ratio, and these carbon-carbon composites become more and more popular due to higher operating temperature and so on, and we are mostly concentrated on the metallic system, and therefore, we are in the development of metal matrix composites and intermetallics with functional properties and higher temperature. And therefore, today you can see that we have discussed about a brief overview of all the materials that has been developed so far and what is the need of their development. At the same time, by 2030, what are the different type of metastable or advanced or functional alloys we need to develop is discussed today, and thank you very much for your kind attention.